In Lesson 6-3, we're going to be talking about that exponential function again, but this time we're going to use many of its applications in the real world to model these functions. Now there's three types of exponential functions, well, more or less two. An exponential growth, notice how this graph is increasing. It starts and keeps going up to the right, whereas our exponential decay starts and goes down to the right. Those are the two basic types of exponential functions. Now you'll note, here's our two basic exponential equations. The main difference is this time, when it comes to real-world applications, oftentimes you're given a rate, like a 20% increase or a 30% decrease. Whenever you're given a percent, we need to remember how to convert it to a decimal. So if I had 56%, we would convert that to a 0.56. That's an old skill that you might have that you're going to use to help convert when it comes to this R. So these equations have been modified. Your rate this time will come from 1 plus the rate they give you as a percentage in decimal form. We always want to use the decimal form of the percent. Now this is for the growth. Of course, we're adding to 1 when we're growing. It's going to get bigger and bigger. Whereas when we have a minus R, it'll be less than 1. It'll be decreasing this way. Keep in mind, your A value is always your initial amount, your starting value. Another formula we'll use is on compound interest. We'll look at this, but remember this whole section is basically going to be taking a real-life application, finding the equation it goes with, and putting in those values in the correct spot. If we take a look at example 3, we're noticing that a video that fans are viewing receives, if it receives 1,000 views per day, it's said to be a favorite video, I guess you could say. So she has a post, this Amelia, where she has 8,192 views on the first day. That will be our beginning amount. So our starting amount, our A, as we call it, our initial is 8,192. We see a rate, we see a percentage here. We're going to use this number. So when our rate is 25%, we know that's a 0.25. So we have, it's decreasing though, because remember when it first is posted, it's amazing. The views are going to go down because people have already seen it. So for our B value, our rate, we're going to use our 1 minus the rate of 0.25. Since it's decreasing by 0.25, we put in our decay rate. So for our equation, once we've identified these variables, we'll have our function will be initial amount times 1 minus the decay rate, or the percentage it was, to the x. Now, they want us to know when it will get below 1,000. In this case, there are times when you'll have an equation and it might say, hey, after 4 days, how many views does it have? In that case, you put the 4 in here and use a calculator to solve this. But they want to know, when will it reach 1,000 views? When will the answer be 1,000, or the y value? So we would put 1,000 equal to this equation. Notice how I've basically just used the basic equation and put in numbers I have for this problem. The best way to solve this from now, instead of algebra, is to type in the 1,000 on our graph. We would graph this monkey right here over on the equation and then plug in the 1,000. When I look for when it's hitting about 1,000, I will need to find where they meet. And you would just use that on Desmos and click where they cross. One other quick example. When it comes to this compound interest, it's the same idea, but they're going to have P for your principal amount, N for the number of days, and R for your rate. Remember that R needs to be in a decimal. A lot of these problems have all their information in a picture. So with our information in the picture, we see the amount we deposit, the initial amount here is $3,000. So that will be our A value. And then the interest rate is 8%. So remember, if we need to convert that to a decimal, that will be 0.08. And if we look at our equation, we're just going to use and plug in the numbers. We've got our principal, our initial amount, 1 plus our rate as a decimal divided by the amount of time to the n. The n would be your amount of periods in a year, how many times we're going to compound the interest. So I apologize about that. T is for time. Looking back here, we've got our 0.08 for our percent, and it's compounded quarterly. So that is our N. Our N is 4 times a year. All right, so if we use our equation, the amount in our equation, put a T there, is our initial amount, 3,000, times 1 plus, and if, again, we're plugging into this equation, 1 plus our rate as a decimal, so 0.08, divided by 4, all to the power of 4 times t. And this case, our t, they want to know how much is in there after 5 years, so we'd multiply by 5. To get our answer, we will just use our calculator, plug in the number, and see what we get. So she would have an amount of $4,457.84. Again, just note how we take information, apply each of those pieces of information into their correct spot, and have our calculator do the math. Now, for part B, we won't do it, but we know that the same amount is her starting principal amount. She's still going to have the same rate of 0.08, but now they're going to compound it annually. That means only 1 time per year. So her number of times compounded would be a 1, and now she's going to have her 15 years, so our time changes. So the main difference here, we again use all these numbers. Our 15 is our time, but compounding annually means once a year. That's why we have the 1. If you do compound this, or do the calculations, you get $9,516.51. Now, in this case, she obviously has more money than if she did it in 5 years, but they want us to compare it to if she did 15 years quarterly. So we'd have another equation with 3,000 times 1 plus the 0.08, with quarterly is 4, and 4 times 15. Doing this gives us $9,843. So we can tell that it's actually better if you compound quarterly or more times a year than just once. For each of these problems in Lesson 6.3, really try to look at what numbers you're given, find which variable they represent, and plug them in. For both of these examples, we had, or for example, the first one we did was an exponential decrease or decay, and this one was an exponential increase.